Welcome back to Chemistry 4300. In this video, we're going to begin Chapter 3, which covers the kinetic theory of gases. Now, many of you will remember from your high school chemistry the equation PV equals nRT. This is the ideal gas equation of state. What we're interested in doing here in this chapter is to try to understand the microscopic origins of this equation in terms of classical physics. That is to say, can we use Newtonian physics, Newton's equations of motions, to understand why this equation has this form. Now, generally speaking, equations of state are derived empirically. That is, many measurements are done and the laws are sort of determined from what we observe. And this began for this equation back in 1662 when Robert Boyle discovered that pressure times volume was equal to a constant for gases at a constant temperature. Many years later, over 100 years later, Jacques Charles found that the volume over temperature of a gas remained constant if you held the gas at a constant pressure. So you could vary V and T as much as you want, but they would always be equal to the same constant if you have the pressure constant. Now, one of the reasons it took so long for this, from between Charles and Boyle, is that we didn't really have good thermometers back in the days of Boyle. It wasn't until the turn of the 18th century, so the early 1700s, that we got thermometers that had the kind of precision that Charles needed to do these kind of measurements. And it wasn't long after that that Amedeo Avogadro discovered that the volume over the amount, the number of moles, was equal to a constant at constant pressure and temperature. And finally, it was in 1834 that Émile Clapeyron brought all of these laws together into the equation of state that you know, the PV equals nRT, introducing the gas constant here. Now, early on, right after Boyle had discovered that PV is equal to a constant, Daniel Bernoulli started thinking about this and thinking, okay, can I come up with some kind of classical physics explanation with maybe some statistics that I can use to explain Boyle's law? Why is that a constant? So what he did turns out to be very insightful, but it wasn't really noticed at the time, back in the early 1700s. It wasn't until Clapeyron had come up with PV equals nRT that we understood the full impact of what Bernoulli's derivation told us. So what we're going to do is we're going to go back through Bernoulli's derivation, which is really quite simple, and then we'll look at PV equals nRT and how it relates to Bernoulli's derivation and what we can learn from that. So the start of this derivation simply goes by trying to figure out the force of a molecule hitting a wall. Then we're going to work out the force of n molecules hitting that wall, and then the force of n molecules hitting all of the walls, and then we're going to convert that force into pressure, and then we'll have our derivation of Bernoulli. So let's start. If we take the one molecule, say moving along the y direction, and we just want to get the force along the y direction, then we can imagine that this is a wall that's perpendicular to the y direction, and as the molecule moves, it hits the wall in an elastic collision. That means that kinetic energy is conserved, and it hits the wall and it flies off with a velocity that's equal but opposite in the y component after that collision. So that means that with linear momentum conserved, that we can calculate the change in the momentum along the y direction as py final minus py initial, which is minus mvy for the final, minus mvy for initial, which gives us minus 2mvy for the change in the momentum along the y direction. Now, for the time, what we're interested in is the average force hitting this wall, so we want to know the time between collisions with the wall. And that, of course, is just going to be the time it takes for the molecule to go across the box, across the y direction of the box, hit the other wall, and come back and hit the wall that we're interested in again. So that time is going to be 2 times the length of the box, there and back, divided by its velocity along the y direction going there and back. So that's going to be our delta t. So taking those two results here and here together, we have the force as delta p over delta t, so we plug in our minus 2mvy, and then for the time we plug in 2l over vy, and that gives us minus 2mvy squared over l. Next we move on to n molecules hitting that one wall, and for that we're going to have to sum over all of those forces, And remember, each molecule is going to have a different velocity. So we're going to have a summation of, for alpha goes from 1 to n, where the alpha particle or molecule would have a velocity of vy alpha. So we're going to take that sum of those vy squared, and all the molecules have the same mass, and the box has the same length, of course. So that gives us the force of n molecules hitting that one wall. Now, if we want to get the force of n molecules hitting all 6 walls, meaning up, top and bottom, left, right, and front and back, then we're going to take the magnitude of this, and we're going to have the x component, and it's going to be times 2 because there'll be 2 walls along x. We're going to have the y component and its 2 walls, and then we're going to have the z component and its 2 walls. So that's going to give us the total force, and I can rearrange that expression to give me this expression where we've pulled all the velocity vector components together, and we recognize that as just the length of the velocity vector squared. So that becomes this expression over here, written in terms of just the magnitude of the velocity vector squared. Now, I can define the mean square velocity as taking all of those molecules' velocities and divided by the total number of molecules to get this quantity here. So for the n molecules, we can define one statistical quantity, which is the mean square velocity. And if I rearrange that expression here to bring the n over, then I can see that n times the mean square velocity is equal to that summation that I have in this expression. So I'm going to go ahead and substitute, and I can write down that the total force now, with this substitution here, is equal to 2 times the mass of a molecule divided by the length of the box times n times the mean square velocity. Okay. Now, let's move on to pressure. We have the total force. We just need to figure out the pressure in the box. And the pressure is the force per unit area. So we need to have the force divided by the total area that the molecules are hitting. So there are 6 walls, so we're going to have the force divided by the area of 6 times the area of one wall. So if we take our result from before, then that's going to be 2 times mass divided by the length times the number of molecules times the mean square velocity divided by 6 times the area of one wall. And if I rearrange that expression, then you can see that the area of the wall times the length of the box is just going to be the volume. So now I can make that substitution, and I have it in this form. And then I'm going to move that volume over to the other side, and now I have the derivation that Bernoulli had, which is PV is equal to a constant, which is Boyle's law, but now Bernoulli had identified the constant as n times the mass times the mean square velocity divided by 3. A little bit of rearranging there, and what you find is that you can write that as 2/3 times n times the mean kinetic energy of a molecule. So we'll write this down as lowercase e bar as 2/3 n times e, which is the mean kinetic energy of a molecule. Now, if we wanted to write this in terms of moles, n is equal to some number. With n is the number of molecules, n is the number of moles, Na is Avogadro's constant. So we can rewrite that expression as PV is equal to 2/3 n, lowercase n, for the number of moles, Avogadro's number times the mean kinetic energy of a molecule. And then, of course, we can then multiply these two guys together, and we'll just call this capital EK as the kinetic energy of 1 mole of gas. So this is what Boyle's law is telling us, that pressure times volume is equal to a constant, which is just related to the kinetic energy of the gas and the number of moles that are present there. So that was the result of Bernoulli. But now we bring in Clapeyron's PV equals nRT equation, and you see what we learn. You see that PV equals nRT, which is now equal to 2/3 n times the kinetic energy of a mole of gas, and we discover, rearranging this, that the kinetic energy of a mole of gas is 3/2 R times the temperature. So this is a constant, R is a constant, so the only thing relating kinetic energy and temperature are just constants, so they're actually one and the same. So the true nature of temperature is that it's just simply a reflection of the kinetic energy of the gas molecules. This also tells us why we can't have negative temperatures, on a Kelvin scale, of course, but you can't have negative temperatures because you can't have a negative kinetic energy. And you see that if you raise the temperature, what you're doing is you're raising the kinetic energy. And if you lower the temperature, you're lowering the kinetic energy. So this is really a fundamental result here. We think about temperature. We have thermometers, which have a scale which is in Celsius or Fahrenheit, and we think about energy with units of joules or calories or things like that. But actually, those are identical in a sense, other than this constant. So it's just sort of historical that we have thermometers that are in units of temperature, like Celsius or Kelvin. But we could have, once we had this understanding, changed all of our thermometers so that they're in units of energy. If we go a little further here, you can see that if we divide this relationship by the Avogadro's number, then we can write down the mean energy of a molecule in terms of R divided by Avogadro's number, which we're going to define as a new constant, which is called the Boltzmann constant. So the mean kinetic energy of a molecule in the gas is 3/2 times kBT, where this kB now is the Boltzmann constant. So we can go a little further with this result. And this is an interesting sort of solution here, is that if you take the kinetic energy with the mean squared speed and you equate that to 3/2 kBT, then you can rearrange this to calculate the RMS speed. So if I take the square root of the mean square velocity, then that gives me the RMS speed. I'm going to use c because speed is a scalar quantity, whereas velocity is a vector quantity, so we don't want to get any confusion there. And so we can take this equation here and rearrange it to get the RMS speed is equal to the square root of 3 kBT over m, or if you want to write it in terms of molar mass, 3 RT over m, square root of all of that. So clearly we see that the speed of the molecules, just like the kinetic energy, is going to be related to the temperature and the molecular mass or the molar mass. And obviously then as you increase the temperature, you're going to be increasing the RMS speed of the molecules. Similarly, if you increase the mass, you're going to be decreasing the molecular speed. So there's an inverse relationship with molecular speed and inverse square root relationship and direct square root relationship to temperature. So finally, let's look at an example calculation with that equation. Let's say we wanted to calculate the RMS speed of a mole of vanillin molecules at room temperature. So that would be relatively straightforward. We just take our equation for the RMS speed. It's 3 RT over m. We know for vanillin it has this formula, so we can calculate its molecular weight, 152.1 grams per mole. Room temperature would be, say, 300 Kelvin. So substituting that all in, you get about 221 meters per second, which, converting it to units you're familiar with, probably would be about 500 miles an hour. Now that's pretty fast. So a vanillin molecule is moving at 500 miles an hour at room temperature. So I'm going to leave this with last question for you then. If I had a bottle of vanilla extract and I open up the bottle and the vanilla molecules are moving at 500 miles an hour, why does it take so long for that scent to move across the room for you to smell it? All right, so we can talk about that in class. So that's it for this part of Chapter 3. In the next video, we're going to be discussing Maxwell's distribution laws.